When dealing with multiple electrical services of different voltages located on the same building, it is essential to use separate ground rods for each service. The primary reason for this is to ensure that the grounding system for each service remains independent. If a common grounding electrode system were used, a fault on one service could potentially induce a ground fault on the other, creating a hazardous situation. The National Electrical Code (NEC) mandates that each service have its own distinct grounding electrode system. This system can be comprised of one or more ground rods, or other approved grounding electrodes, driven into the earth. These ground rods should be spaced at least 6 feet apart to ensure effective dissipation of fault current and to minimize the potential for ground potential rise issues. The connection between the ground rods and the service panel must be made using a copper grounding conductor of appropriate size, as determined by NEC Table 250.66, based on the size of the service entrance conductors. The purpose of the grounding electrode system is to provide a low impedance path for fault current to return to the source, facilitating the rapid operation of overcurrent protective devices such as circuit breakers or fuses. This helps to limit the duration of the fault and minimize the potential for damage to equipment or injury to personnel. Using separate ground rods helps to isolate each service's grounding system, preventing a fault on one system from affecting the other. This isolation is particularly important when the services operate at different voltage levels, as a fault on the higher voltage system could pose a significant hazard to the lower voltage system if they were interconnected through a common grounding electrode. The NEC specifies requirements for the size and type of grounding electrodes, as well as the grounding electrode conductor that connects the electrode to the service equipment. Ground rods must be at least 8 feet in length and have a minimum diameter of 5/8 inch, unless otherwise listed. The grounding electrode conductor must be sized according to NEC Table 250.66, based on the size of the service entrance conductors. It is also important to ensure that the ground rods are installed in soil that has a low resistivity, which will improve their effectiveness in dissipating fault current. If the soil resistivity is high, it may be necessary to install additional ground rods or to use other grounding electrodes, such as ground plates or concrete-encased electrodes. The NEC also permits the use of the building's metal water pipe as a grounding electrode, but it must be supplemented by an additional grounding electrode, such as a ground rod. This is because the water pipe may be disconnected or replaced with non-metallic pipe, which would compromise the grounding system. In addition to the grounding electrode system, each service must also have an equipment grounding system, which is used to ground the non-current carrying metal parts of electrical equipment, such as enclosures, raceways, and motor frames. The equipment grounding system is connected to the grounding electrode system at the service equipment. The purpose of the equipment grounding system is to provide a low impedance path for fault current to return to the source, even if the fault does not involve the grounding electrode system. This helps to ensure that overcurrent protective devices will operate quickly to clear the fault. The equipment grounding conductor must be sized according to NEC Table 250.122, based on the size of the overcurrent protective device protecting the circuit. It is important to note that the equipment grounding conductor must be installed in the same raceway or cable as the circuit conductors. This helps to minimize the impedance of the grounding path and to ensure that fault current will flow quickly and effectively. In summary, when installing multiple electrical services on the same building, it is essential to use separate ground rods for each service. This will help to ensure that each service has a safe and reliable grounding system, and that a fault on one service will not affect the other. The NEC provides detailed requirements for the design and installation of grounding electrode systems, and it is important to follow these requirements carefully to ensure the safety of the electrical installation. Installing separate ground rods ensures each service has its own dedicated path to ground, minimizing the risk of fault current flowing through unintended paths. This is particularly crucial in scenarios where different voltage levels are present, as a fault in a higher voltage system could create a dangerous situation for a lower voltage system sharing the same ground. The spacing of at least 6 feet between ground rods is specified to prevent one ground rod's zone of influence from negatively affecting the performance of another. The copper grounding conductor plays a vital role in providing a low impedance connection between the ground rod and the service panel. Its size is determined by the size of the service entrance conductors to ensure it can handle the potential fault current. Regular inspection and maintenance of the grounding system are crucial to ensure its continued effectiveness. This includes checking for corrosion, loose connections, and damage to the ground rods or conductors. Soil conditions can also affect the performance of ground rods. Dry or sandy soil may have higher resistance, requiring additional ground rods or alternative grounding methods. The NEC provides guidance on how to address these situations. In addition to ground rods, other types of grounding electrodes can be used, such as ground plates, underground metal water pipes, or concrete encased electrodes, often referred to as UFA grounds. When using a metal water pipe as a grounding electrode, it must be supplemented by another type of electrode, such as a ground rod, to ensure redundancy and reliability. This is because water pipes can be replaced with non-metallic materials, which would compromise the grounding system. The equipment grounding system is an integral part of the overall grounding strategy. It connects the non-current carrying metal parts of electrical equipment to the grounding electrode system, providing a path for fault current to flow back to the source. This helps to quickly trip over current protection devices and prevent electrical shock hazards. The size of the equipment grounding conductor is determined by the rating of the overcurrent protection device protecting the circuit. It must be installed in the same raceway or cable as the circuit conductors to minimize impedance. Bonding is another important aspect of grounding. Bonding involves connecting all metal parts of the electrical system together to create a common ground potential. This helps to prevent voltage differences between different metal parts, which could create a shock hazard. The NEC provides detailed requirements for bonding, including the size and type of bonding conductors. Surge protection is also related to grounding. Surge protective devices, or SPDs, are used to protect electrical equipment from voltage surges caused by lightning or other events. SPD are connected to the grounding system to provide a path for surge current to flow to ground. The effectiveness of an SPD depends on the quality of the grounding system. A poor grounding system can limit the ability of an SPD to protect equipment from surges. Therefore, it is crucial to ensure that the grounding system is properly designed and installed when using SPD. Ground fault circuit interrupters, or GFCIs, are another important safety device that is related to grounding. GFCIs are designed to detect small ground faults and to quickly interrupt the circuit, preventing electrical shock hazards. GFCIs work by monitoring the current flowing in the circuit conductors. If there is a difference in current between the hot and neutral conductors, it indicates that some current is flowing to ground, which could be due to a ground fault. The GFCI will then quickly trip the circuit, preventing a shock hazard. GFCIs are required in many locations, such as bathrooms, kitchens, and outdoor areas, where there is a high risk of electrical shock. In addition to separate ground rods, it is also important to ensure that the electrical panels for each service are properly labeled. This will help to prevent confusion and to ensure that workers can easily identify the correct panel when performing maintenance or repairs. The labeling should clearly indicate the voltage and amperage of the service, as well as the location of the main disconnect. Proper grounding is essential for electrical safety. It helps to protect people from electrical shock, to prevent damage to equipment, and to minimize the risk of fire. By following the NEC requirements for grounding and by using qualified electricians, you can ensure that your electrical system is safe and reliable. Remember to always consult with a qualified electrician when working on electrical systems. Electrical work can be dangerous, and it is important to have the knowledge and experience to do it safely. Never attempt to perform electrical work unless you are properly trained and equipped. Always turn off the power before working on any electrical equipment. Use insulated tools and wear appropriate personal protective equipment such as gloves and safety glasses. If you are unsure about anything, consult with a qualified electrician. Ignoring proper grounding procedures can lead to serious consequences, including electrical shock, fire, and equipment damage. Protect yourself and others by taking the necessary precautions and following the NEC requirements for grounding. Firstly, understand the NEC requirements for grounding electrode systems. Secondly, ensure proper spacing between ground rods. Thirdly, use appropriately sized copper grounding conductors. Fourthly, consider soil conditions and resistivity. Fifthly, supplement water pipe electrodes with additional grounding electrodes. Sixthly, maintain a robust equipment grounding system. Seventhly, implement proper bonding techniques. Eighthly, consider surge protection measures. Ninthly, utilize GFCIs in high-risk areas. Tenthly, ensure proper labeling of electrical panels.